In class, we began talking about states and superpositions, and we worked our way up to the Born rule, which is the fundamental rule of probability in quantum mechanics. In this lecture, we're going to go a little bit further, and we will begin by reviewing some of what we said in the lecture in class. So we said that quantum observables are quantities that we can measure or test. And when we measure or test them, we get numerical results. So polarization is an example, momentum is an example, angular momentum is an example. We will meet another kind of quantity this time. But the term observable here simply means that it's something that we can go into the lab and measure or test. Quantum states are controversial in one sense, but in another sense, they're not controversial at all. When physicists in their day-to-day setting talk about quantum states, they're talking about what it is that allows us to figure out the probability that a quantum mechanical measurement will have a certain outcome. So, for example, a state might tell us that the probability is, let's say, 3/4, that if we test the polarization of a photon in a particular direction, call it x, that we'll find the result 0. That's the kind of thing that states tell us. Now, for any quantum observable, there is a set of possible measured values, the outcomes you could get when you measured it. And we will call those the eigenvalues of the quantity, the eigenvalues of Q. And there's a set of mutually orthogonal, that is mutually perpendicular vectors. For each of the eigenvalues, there will be an eigenvector. And we will restrict ourselves to eigenvectors that have length 1. If you can find eigenvectors, you can find eigenvectors of length 1, but for reasons that have to do with not having to repeat certain things constantly, when we use the word eigenvector, we will mean a length 1 vector that represents a particular possible outcome of a measurement of a quantum observable. So each eigenvalue will have its own distinct eigenvector. Two different eigenvalues, let's say 1 and 0 for polarization in a particular direction, go with two different mutually orthogonal eigenvectors. And then we come to the state vector. The state vector tells us probability information. It represents the state of the system. It's a length 1 vector. We'll call a state vector psi many times because that's a common thing for you to find when you are looking at literature on this. Greek letters are often used for state vectors. Psi is a length 1 vector, and it's an eigenvector of some observable or other, but which one will depend on the circumstances. And in any case, even though psi is an eigenvector of something or other in every case, usually whatever it is that we're going to measure isn't what psi is an eigenvector of. And so you don't really need to worry about that, except to keep in mind that state vectors and eigenvectors aren't two different kinds of things. So if we've got an observable, call it Q. If Q1, Q2, and so on are the eigenvalues of the observable, and the corresponding eigenvectors are these vectors here, which we'll also call Q1 and Q2, we can write the vector psi as a sum of these eigenvectors. We'll be able to find numbers C1, C2, and so on that make psi into a vector sum of the Qi vectors multiplied by appropriate numbers. This means we're writing psi as a superposition of the eigenvectors of Q. We could write psi as a superposition of any quantity we liked, and we're just saying suppose that quantity is some quantity Q. Now, if we measure Q, we know that we'll get one of the results Q1, Q2, etc. Psi gives us the probability. It gives us the probability through this formula. The probability that a measurement of Q will have the result Q1 is the absolute value of C1 squared. The probability that the result will be Q2 is the absolute value of C2 squared, and so on. You might wonder why I talk about the absolute value and why I don't just say the square. That will come up later. This rule that we've just stated here is the Born rule, named after the physicist um, Max Born. It is the most important quantum mechanical rule that you are going to encounter. Now, quantum angular momentum is an example that we can use to kind of see how this works. We talked about it in the lecture, but we will review quickly here because it's a nice transition to our further example. Well, angular momentum is the kind of rotational momentum that something has when it's rotating around an axis. And when you think about classical things like a spinning ball or a spinning top, the angular momentum around the axis takes a whole continuum of values. It might have a minimum possible value, it might have a maximum possible value, but any of the values in between, any of them, all infinitely many, they're all possible. That's not how it works quantum mechanically. Quantum mechanically, if you have an object that has angular momentum, then the possible values are discrete. They aren't continuous. And in fact, typically they're going to be confined to a certain range, or at least often they will. So we're going to imagine that we have a quantum system that has angular momentum, and no matter what direction we pick to measure that angular momentum in other words, we look at a certain axis and we ask what's the angular momentum around that axis, well, we're imagining that for this particular system, there are only three possible answers: -1, 0, and +1. This is a perfectly possible kind of quantum mechanical situation. So no matter what direction we pick, call it x, call it whatever you like, there's an angular momentum observable. Angular momentum around that axis, or as we say, angular momentum in that direction. The eigenvalues for that angular momentum observable are -1, 0, and +1. And so we're going to look a little further and see how this connects up with what we said about states and eigenvectors. And we're going to think about two directions, z and x, and we're going to imagine that they are perpendicular or orthogonal directions. Well, let's suppose that in this quantum state of this particular system, it's certain that if we measure the angular momentum in direction x, we'll find +1. In other words, the state of the system, the quantum state of the system, is this vector x plus, the +1 eigenvector for angular momentum in the x direction. We can write the state as a sum of the z eigenvectors, the z angular momentum eigenvectors. And if we do, quantum mechanics tells us that this is what we'll get. These numbers are the coefficients for these eigenvectors of z angular momentum. So now we know the probabilities if we make a measurement of z angular momentum. The probability we'd find -1 is this squared. The probability we'd find 0 is this squared. And the probability we'd find +1 is this squared. It always works that way. The numbers, of course, will change with the example, but the general idea stays the same for any quantum state and any observable. Now, I caution you here, we've talked about this before, that these vectors don't have a direct spatial meaning, okay? We can't think of state vectors as representing directions in physical three-dimensional space. They have a more abstract meaning. They go along with possible outcomes of an experiment, and they're related to probabilities. But now we're going to go on to a different example, and we'll take a pause here because this example introduces a new feature of quantum states that you might not have expected. So back in the next part of the lecture with the example of quantum spin half.